Today, we are going to tackle one of the most common and, let's be honest, frustrating problems in machine learning: overfitting. It's that thing where your AI model looks like an absolute genius during training, but then completely bombs its first real world test.
So let's just start with this one. Simple question. What if that brilliant AI model you spent all this time building isn't actually learning anything? What if it's just gotten incredibly good at, well, memorizing the answers to the test? That right there is the core of overfitting, and it's what we're breaking down today.
Okay, let's start with the symptoms. You've trained your model, you're looking at the performance metrics, and they look fantastic. You're thinking, yes, I've nailed it. But so often, lurking just beneath the surface is a model that hasn't learned a thing. It's just memorized every single training example, warts and all, including all the random noise. And this right here is the classic sign of trouble. On the data it's already seen, the training set, the model is nearly perfect. But the moment you introduce it to new, fresh data it's never seen before, its performance just falls off a cliff. This massive gap is the absolute signature of overfitting. So let's put a clear definition on this. Overfitting is what happens when a model gets a little too obsessed with the training data. Instead of learning the general underlying patterns, the stuff we actually care about, it memorizes every little detail, every quirk, and even the random noise that's only present in that specific dataset. And this is why it's such a big deal. The model completely fails to generalize. Generalization is the whole point of machine learning, right? We want to build something that can make smart predictions on data it's never encountered. Overfitting is a total failure to do just that. So we know what it is, but how do we catch this thing in the act? Well, thankfully, the data itself leaves behind a trail of clues. We just need to know where to look and which performance metrics will tell us the real story. And this is the key question every single one of us has to ask. How can you be totally confident that your model is overfitting and not just, a bad model in general? The answer is all about comparison, specifically comparing its performance on two very different sets of data. And here it is, the smoking gun. Just look at these numbers. During training, the accuracy is an incredible 99%, and the loss is super low. Amazing, right? But then you look at the validation set. That's the data it hasn't been trained on, and the accuracy just plummets to 72% while the loss totally skyrockets. When you see that validation metrics are so much worse than your training metrics, yep, that's overfitting. But here's the good news. This is absolutely a solvable problem. It's so common that we've developed a whole toolkit of strategies to fight back and push our models to actually learn instead of just getting lazy and memorizing. We're going to walk through 4 of the heavy hitters. First, the simplest one, just adding more data. Second, a pretty cool technique called data augmentation. Third, we're going to simplify the model itself. And finally, a really clever method called dropout. All right, strategy number 1 is often the most effective, and it's dead simple. Get more data. The more diverse and varied examples you can show a model, the harder it is for it to find little quirks to memorize. It's forced to look for the real general patterns that hold true across everything. Here's a perfect example. Imagine you're training a dog classifier, but your dataset is only pictures of big dogs, like labs and boxers. The model might just learn that dog equals large with short fur. So what happens when you show it a tiny, fluffy Pomeranian? It's going to be completely lost. The fix? Add more variety. Pictures of Chihuahuas, poodles, and yep, Pomeranians, to teach it what dog really is. But what if you can't just go out and find more data? It can be expensive or time-consuming or just plain impossible. Well, that's where data augmentation comes to the rescue. It's a fantastic trick where you create new training data by making small, realistic tweaks to the data you already have. Let's see exactly how this works. We can take just one single picture of a dog to start with. Now, from this one image, we can cook up a bunch of new training examples. We can flip it horizontally, so now the dog is facing right. We can rotate it just a little bit. We could zoom in and crop it. To the model, each one of these is a totally unique picture. We're basically expanding our dataset for free and teaching the model that a dog is still a dog no matter how you look at it. Okay, our third strategy is to kind of rein in the model itself. Sometimes the problem is that our model is just too complex. It has too many layers, too many neurons. It has so much capacity that memorizing is actually the easiest thing for it to do. By making the model a little simpler, we can actually restrict its ability to memorize, forcing it to find those more general, important patterns.
And last but not least, we have one of the most popular and, frankly, most ingenious techniques out there: dropout. Here's the idea. During each step of the training process, the model randomly drops out or just temporarily ignores a few of the neurons in a layer.
So why does this work? It's actually brilliant. It stops any one neuron from becoming too specialized or relying too heavily on its neighbors. It's kind of like forcing a team to work together, but you never know which players might be out sick on any given day. Everybody has to learn to pull their own weight. This makes the whole network much more robust and way less likely to overfit.
So as we wrap this up, let's just circle all the way back to that core idea. Everything we've talked about today, the problem itself, how to spot it, how to fix it, it all boils down to one fundamental difference.
And this quote just says it all. A model that only memorizes is basically just a fancy searchable database. But a model that can generalize, that's a model that has actually learned something useful and meaningful about the world. And that is always the goal. So the next time you're building a model and you see those amazing scores, just pause for a second. Ask yourself this: is my model truly learning how to solve this problem? Or did it just get really, really good at passing the test? Trust me, the answer to that question makes all the difference in the world.